So our first limit, the limit is x approaches 0 of 3x over the cube root of x plus 8 minus 2. What's the first thing we should do with this limit?
Plug it in and see if it's indeterminate.
Plug it in, see if we get a number or if it's indeterminate. So plug in 0, the numerator is 0. And the denominator, cube root of x plus 8. If we plug in 0, that's just the cube root of 8, which is 2 minus 2, 0. So it is indeterminate, unfortunately, because if it wasn't indeterminate, then we'd be done. So what are we going to do to deal with this one? Because it doesn't quite look like any of the ones we've dealt with yet.
Could you start by like cubing everything?
So that's a good thought, but unfortunately, no, because if you cube everything, you're getting rid of, part of what this function is. You're altering the function. So if you cubed it and cube rooted everything, then that'd be okay. But doing that wouldn't actually end up helping. Also, if we tried to cube the denominator, it's cube root of x plus 8 minus 2 that would be cubing. So we'd have to multiply that by itself 3 times, and that's. I know your idea was to get rid of the cube root, but unfortunately that doesn't clear it out. So it's a good thought though. Any other ideas, anybody?
Maybe you could like move the minus 2 somewhere else by writing it as a different limit.
That's a good idea. We've separated stuff out. But all the ones that we've separated out so far had like a plus or a minus in the numerator, if we were separating them using addition. And then we were able to make it like the first part of the numerator over the denominator, and then the second part of the numerator over the denominator, added or subtracted. But in this case, we just have one term in the numerator and 2 terms in the denominator. We can't, if we have 1 over 2 plus 3, that's not the same as 1/2 plus 1/3, right? So we can't do that. Again, it's a good thought. What are some other tricks we've done? Factoring. I don't see any way to factor that. Anybody see a good way to factor that? No, me neither. And we also tried multiplying stuff by the conjugate. So we could try multiplying by cube root of x plus 8 plus 2 to both the numerator and the denominator, but that's not going to clear out this cube root because that only works with square roots. So we're kind of stuck. There's only one other trick that we've used. We did it with some trig limits. That's going to help us here. It's same idea as something we did, but not exactly the same. So remember when we
split the numerator?
So like into 3 over times x over that? As in like this?
Yeah.
So again, that's a good idea, but unfortunately it's not going to end up working out. Because if we try to split this into 2 separate limits this way, the first one is 3 over 0, which is undefined, and the second one is still 0 over 0, so it's still indeterminate. That's a good idea. So remember when we had this, or something like this, and it was 0 over 0, but it wasn't quite the sine x over x that we needed it to be 1. What did we do with it?
Like you multiplied the bottom by like 1 over 5, and then you took like the 5 out.
Okay, right. And then we were left here, which was good. And then we still had an issue with this being sine 5x over 5x. And how did we, for the very first time, deal with that?
A u substitution, you set 5x equal to u.
Right, exactly. And we had this issue. We had these terms in here, these 5x's that were giving us a problem because they weren't the x's that we needed them to be. And so using a similar idea of a u substitution, what is giving us the biggest issue in this limit? What's the most, the piece that's the biggest pain to us, you think? What would you like to not see in there?
Cube root of x plus 8.
Yeah, probably a cube root of x plus 8, right? I mean, most people are okay with a 3x and a minus 2, but a cube root of x plus 8 seems like a pain. So let's just get rid of it. Let's let u equal cube root of x plus 8. We'll have a limit. Okay, it does not look like a limit as x approaches 0, a 3x over u minus 2. So that's great, but we now have the issue of having x's and u's. So what do we need to do? We need to convert this x approaches 0 into a u approaches something, and convert this x into something in terms of u. Everybody good with that so far? Okay, so as x approaches 0, what is u approaching?
2.
2, right. All we got to do is plug in 0 into our u formula. 0 plus 8 is 8, cube rooted is 2. So if x is approaching 0, u is approaching 2. So we'll rewrite this as a limit as u approaches 2 of something over u minus 2. 3x, right? But the x is going to be a problem. If this limit is approaching, or u approaching 2, and it's got a u in the denominator, we need to have some u's in the numerator too, probably, right? So what does x equal in terms of u?
U cubed minus 8.
Exactly. We're going to go back to this original u equals cube root of x plus 8. We'll cube both sides to give us u cubed on the left and x plus 8 on the right, and then subtract the 8. So u cubed minus 8 equals x. And we'll replace the x with u cubed minus 8. Everybody good with that?
Yeah.
Any questions? Very good. All right, now all we have to do is plug in the 2, right? What happens when I plug in the 2? What do you get?
Still 0 over 0.
Still 0 over 0. So at first glance, it's like, oh, that work was for nothing, but not really, because now I'm looking at a polynomial divided by a polynomial. And with any luck, I should be able to factor out that numerator, shouldn't I? How does u cubed minus 8 factor? It's a difference of cubes, isn't it? How does u cubed minus 8 factor? U minus 2, u squared plus 2u plus 4. If you don't remember your differences in sums of cubes, you need to take a look at the paper that I posted up in Google Classroom. Make sure you know them. Now the u minus 2's will cancel, and we're left with 3 times, what is that, 4 plus 4 plus 4, or 36. Any questions, problems, issues? Anybody having a problem with that one?
So would you just would you use this method whenever when you see like a root in the denominator, or or does it like have to be a cube root? It's just
Yeah, I mean, generally, if we're looking at a cube root, you're going to want to substitute. If you plug it in and you get 0 over 0, you're going to want to go in and you're going to want to substitute out that cube root. Anytime you've got something that's indeterminate and you don't see a nice, simple, easy fix like using factoring or multiplying by the conjugate for it, you're pretty much going to want to go ahead and do a u substitution for the thing that's messy, the thing that makes it an issue.
Okay.
Yeah.
Got
Any other questions on that one? All right, let's look at another one. What's the first thing you should do?
Plug in x.
Plug in our x equals 0 value. What do you get if you plug in 0? Should get, plug in 0, this is 27 cube rooted, which is 3, squared, which is 9, okay, minus this, which is 18, plus 9 over 0. That's 0 over 0, right? Everybody agree that that's 0 over 0? Hope so, because it is. So then what? What's the mess? What's causing the issue here?
The cube roots.
Cube roots. So let's get rid of the cube roots. Let's let u equal cube root x plus 27, which tells us that x is equal to u cubed minus 27. And as x approaches 0, u approaches what?
3.
3, exactly. So we can rewrite this whole thing as the limit as u approaches 3. And we're getting rid of just the cube root of x plus 27 here. So that becomes what? That first term in the numerator becomes u squared. And then minus 6u plus 9. And then down here we got x squared, or u cubed minus 27 squared. Everybody good with that so far?
Yes.
All right, cool. Now we just need to factor the numerator. What does the numerator factor to?
U minus 3 squared.
U minus 3 squared. And our denominator, once again, is a difference of cubes. So u cubed minus 27 is u minus 3, and u squared plus 3u plus 9. And we're squaring u cubed minus 27, which means we're squaring both pieces of that. Everybody good there?
Yep.
Okay, the u minus 3 squareds cancel. And now we can just plug in our 3 value, which that gives us 9 plus 9 plus 9 down there in the denominator, squared. 27 squared is what? That's right, 729. Any issues with that? Any questions? Everybody feel okay about that one? All right, let's look at another one. It's a limit, so what's the first thing we should do?
Plug in x equals 1.
Plug in the 1. What do you get if you plug in 1? You get 0 over 0, right? 1 to the 1/8 power is still 1. Minus 1 is 0, and 1 minus 1 is 0. Everybody agree that's indeterminate, 0 over 0?
Yes.
Yes.
Mm-hmm.
Perfect. So what is the biggest mess of this? What is the thing you don't want to deal with?
1/8 power.
Yeah, x to the 1/8 power. Who wants an x to the 1/8 power? Nobody wants to deal with that. So don't deal with it. Let u equal x to the 1/8. If u is x to the 1/8 and x is approaching 1, then what's u approaching?
1.
Also 1, right? 1 to the 1/8 power is 1. And we're also going to need to figure out what does x equal. So if u is x to the 1/8, what is x equal?
U to the 8th?
U to the 8th, right? To clear out the 1/8 power, you got to raise both sides to the 8th power. So x to the 1/8 to the 8th is x, and u to the 8th is u to the 8th. So we got limit as u approaches 1 of x to the 1/8 was our u, so u minus 1, and in the denominator, u to the 8th minus 1. And then hopefully all we have to do is plug in the 1, but unfortunately when we plug in the 1, what do we get? We get 0 over 0, so we're going to have to do some factoring. The bottom is what? What special case is the bottom?
Difference of squares?
The difference of squares, right? U to the 8th is just u to the 4th squared. So that becomes u to the 4th plus 1 and u to the 4th minus 1. Do we have anything that cancels out yet? Sure doesn't look like it, right? So the u to the 4th minus 1 should factor a little bit more. It's still a difference of squares, right? So what does u to the 4th minus 1 factor to? U squared plus 1 and u squared minus 1. And still nothing to cancel, so we'll keep factoring. I almost made that fit there on the screen. And now that we finally got it all the way factored down, the u minus 1s will cancel, right? Everybody good with all that factoring and canceling and all that? Plug in 1 over 2 times 2 times 2, 1 over 8. Any questions on that one? Everybody good there? All right. I'm going to assume that's a yes since nobody's responding. Either that or nobody can hear me. So let's change gears slightly. And instead of talking about limits, well, we're still going to talk about limits, but we're going to talk about continuity. You guys are familiar with what it means for a function to be continuous, right?
Yes.
How would you describe a function that's continuous?
It doesn't have any holes or asymptotes.
No holes, no asymptotes, right? No breaks in the graph. It just goes on and on and on forever, right? And never has any gaps. That's exactly right. So we're going to say a function is continuous if it has no breaks, no holes, and no vertical asymptotes. So in order for us to determine if a function is continuous at, we're going to say at a specific point, and for a function to be continuous at a specific point, any point on that function, there are 3 criteria that have to be met. The first is the function has to be defined at that point, which seems pretty self-explanatory, right? A function can't be continuous at a point if the point doesn't exist. The second thing is that the limit as x approaches c, whatever that point is, has to also exist. And thirdly, both number 1 and number 2 have to be equal to each other. So the function has to exist, the limit at that point has to exist, and the limit and the value of the function have to be equal to each other at that value of c for a function to be continuous. Does that make sense or no?
Makes sense.
All right. So you're probably familiar with some types of discontinuities. I know you already mentioned a couple. Somebody said asymptotes, right? An asymptote is something that gives us a discontinuity. The type of discontinuity is an infinite discontinuity. And I'm gonna have pictures of all these on the next page. But so we have infinite discontinuities. And then somebody said a hole. Holes make what we call removable discontinuities. Anybody know the third type of discontinuity?
Isn't it like a sharp point or something?
I don't know what that means.
Like an absolute value.
Like a corner or something?
Yeah.
Is that what you're saying? No, those are still, you're still continuous at those points.
Isn't it a jump discontinuity?
It is, it's a jump discontinuity. So our three different types are removable, of which there are two different types. There's jump, and there is an infinite discontinuity. Okay? So removable discontinuity just means there's a hole in the graph. Whether we have a defined value for that point elsewhere doesn't really matter. It's still a removable discontinuity. A jump discontinuity is where we're going along and then all of a sudden we stop and jump up to some other point and then continue from there. And then an infinite discontinuity is when we have our vertical asymptote. So I want to quickly think about our criteria for continuity and each of these cases. So the first removable discontinuity, where we just have the hole, does it meet the first criteria? Is f of c defined? Is f of c defined on this first removable discontinuity?
No.
No.
No. So immediately it doesn't meet criteria number one, so that's that. Right. What about this second removable one? Does the function exist at c?
Yes.
Yes, so meets the first criteria. Second criteria, does the limit exist?
No.
No.
The limit doesn't exist?
It exists.
Because the line goes up to it.
Right, the limit exists, right? The limit as x approaches c exists, right? From the left-hand side, I'm approaching some value, and from the right-hand side, I'm approaching that same value. That limit exists. But is that limit the same as the value of the function, the third criteria? No. So
No.
this one immediately fails number one. This one passes 1 and 2, but fails number 3. What about our jump discontinuity? Does the function exist at c?
Yes.
Yes. Does the limit exist at c?
No.
It does not, right? Because from the left-hand side, it's got a limit from the left, right? And it's got another limit from the right, but those two limits are not the same. And therefore, the two-sided limit can't exist. And so this jump discontinuity fails the second criteria. Does that make sense to everybody?
Yes.
Okay. And for our third, or for our last type here, our infinite discontinuity, does it meet the first requirement? Does the function exist at c?
No.
No.
Nope. So immediately we know it's a discontinuity. All right. Everybody good with that? We see the reasons why we have those discontinuities?
Yes.
All right. And remember, the removable ones generally will occur in rational functions, generally, right? When the numerator and the denominator both equal 0 at the same x value. And then the infinite discontinuity, again, is generally in rational functions. There are other cases, but any time where the denominator only equals 0 at c, but the numerator equals an actual value. Then jump discontinuities, we'll see those mostly with like piecewise defined functions. So. All right. Let's take this idea of continuity and apply it into a theorem, the intermediate value theorem. Have you heard of the intermediate value theorem before?
I have not, but
No? I got 1 no and 29 no responses.
No.
I've heard of it.
All right, some people have heard of it then, and some people have not. You may or may not have talked about it. It doesn't really matter. It's a pretty straightforward theorem. It says if I have a function that's continuous on a closed interval from A to B. Okay. And I choose some number, we'll call that number W. And W happens to be between f of A and f of B. That I know somewhere between A and B, there is an X value that when I plug it into my function, gives me W. Sounds a little bit convoluted, probably. But all it's really saying is, if you have a function that's continuous from A to B, pick any number between f of A and f of B, and you can get that number by plugging in something between A and B. It means that every value from the bottom y to the top y gets hit as we go through here. There's no way, if I have a continuous function, for me to get from here to here without touching every value, every y value from f of A to f of B, unless I pick up my pencil. Would you agree?
Yes.
Yeah, that's all this theorem is saying. It's saying if I want to go from this y value to this y value without picking up my pencil, I have to hit every y value in between. I might hit some of those y values more than once, right? I could do that. Perfectly okay. But still, for every y value between f of A and f of B, I still can get it from some number between A and B. Good or no?
Good.
Good. All right. I like to hear that. Good. So the most recognizable consequence of this that we use is if I have some function like this, where let's say I go from x equals -1 to x equals 5, and f of -1 is negative and f of 5 is positive. That tells me that somewhere between -1 and 5, as long as this function is continuous, I must cross through the x-axis. There must be a root there somewhere. Okay? So we'll often use it to find roots or zeros of a function. But that's not the only thing we'll use it for. Everybody good on the basic idea of what the intermediate value theorem is?
Yes,
Yeah.
but does it work for both like x and y values? Like, could it say it hits every x value and also every y value, or like how would you?
So the specific idea of this theorem is that I can choose any y value I want on this interval of y's, and I know that I'll find it in those x's. But yeah, I mean, it doesn't exactly go vice versa, because if I choose any value between A and B, that does not guarantee me that I'm getting a value out between f of A and f of B, right? Like if I draw my picture like this, some of the values I choose, like suppose I chose this one, that doesn't give me a value between f of A and f of B. So it only works this one way, where we can choose any y, and if we pick any y value, we know that we can obtain it by using any x value.
Okay.
Now, it's not to say that that's the only way to get it, right? Because this function might drop back down like this again. And if I picked this W value, I could get it at C, which is between A and B, or I could get it over here at whatever this value is, right? Because I'm hitting W there also. But it's saying that I could get it from some value between A and B. Everybody good? Any questions on that? All right. Let's see if we can take a simple function and verify the intermediate value theorem. Are we ready to do that? Do you think? Let's see. What do you think the first thing we'll need to do is?
Determine if it's continuous over the interval.
Exactly. So first we want to know, is our function continuous? Well, is -x continuous on 0 to 2?
yes.
Should be, right? Why is it continuous? What makes it continuous? Simply enough, just because it's a polynomial. All polynomials are continuous for all real numbers. Okay? Simple fact you'll want to know and memorize. If it's polynomial, it is 100% continuous for all real numbers. And that is a good enough justification for why this function is continuous on the closed interval from 0 to 2, because it's a polynomial. Everybody good with that? Okay, hopefully so. Next thing, what do you think the next thing that we're going to need to do is?
Plug in 0 and then 2.
Yep, plug in 0 and 2. So what's f of 0?
0.
And what's f of 2?
-8.
-8. Good. So now that we've found those values, we should be able to say that by the intermediate value theorem, for any w, or for every w that I choose that is less than 0 but greater than -8, there should exist a c on what interval? On the interval from where to where?
0 to 2 inclusive.
0 to 2, and it's non-inclusive actually. The result of the intermediate value theorem is always on open intervals, even though the function has to be continuous on the closed intervals. So we're going to say there exists a c on the open interval from 0 to 2, such that f of c is equal to w, so that if I plug in c to my function, I should get out that w value. Okay, so this is not verifying that it's true. This is just stating what should be true. So the question then becomes, how do I verify that that's the case? Well, I need to pick every w between 0 and -8 and show that if I use that value, I can, or if I want to obtain that value, I can obtain it using a c value between 0 and 2. Thoughts on how we'll do that? Because I can't just pick every value between -8 and 0, right? There are an infinite number of values between -8 and 0 to test, and that'll take kind of a long time if we try to do all of them. So what do we want to show? We want to show that for w between -8 and 0, c is less than 2, greater than 0. Any ideas on how to do that? Any thoughts?
Could we use a limit?
That's a good idea, but we don't need to. It's a good thought. Makes sense, especially since this is all about limits here so far. But no limits needed. What does w equal?
Is it C?
F of c is w, but w itself is not c. F of c is w. So w equals f of c. What is f of c?
The Y value?
It is the y value, but more specifically, here's our function. Here's f of x. What's f of c?
-c³.
Right. So what does w equal?
-c².
2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2
Negative C cubed.
Right, W equals negative C cubed. Right, F of C is negative C cubed, F of C is W. So we end up with, if I replace the W with negative C cubed, we end up with a new inequality, negative 8 is less than negative C cubed is less than 0, which we should be able to undo and turn into an inequality that shows that C is between 0 and 2. We'll first divide by the negative 1 to get 8 is greater than C cubed is greater than 0. Then we'll cube root and have the inequality C is greater than 0, C is less than 2, which is exactly what we wanted to show. That for every W between negative 8 and 0, C is between 0 and 2. Does that make sense how we did that? We took our F of C value, which is equal to W, replaced the W with F of C, and then solved that inequality for C. Any questions? Anybody got a problem with that? Everybody okay with that? Very silent out there today. It's concerning. I guess we'll move on to the next one if nobody has any questions. We want to show that this function has a 0 between 1 and 2, and we're going to use the intermediate value theorem to do that. So, any thoughts on what we should do first?
Plug 1 in and then plug 2 in.
Okay, even before we do that, one
Figure out
thing we,
continuous.
what?
Figure out if it's continuous.
Yeah, we got to show that it's continuous. And we know it's continuous. We'll say f is continuous because it's a polynomial. And then we'll plug in those values of 1 and 2. So f of 1 gives us what? What is f of 1?
-5.
I disagree. I think it's -4. Yeah, -4 sounds good. 1 plus 2 is 3, minus 6, -3, -1, and then -4. And then what about f of 2? 2 to the 5th is 32, plus another 2 times 2 to the 4th, that's 64, minus, what is that, 48 makes 16, plus 4 is 20, minus 3 is 17. So f of 2 is 17. So, since this function is continuous, we know that f of 1 is -4 and f of 2 is 17. It means that for any w on the interval from -4 to 17, there should be, we'll just say, not even, we won't say there should be, we'll say there exists a c on the interval 1 to 2 such that f of c equals w. Now this time we don't have to go through and verify the whole thing. We know what w specifically we're looking for, right? What w are we looking for? We want to know that it has a 0. So w equals 0 is on -4 to 17, which means that there must be some value of c between 1 and 2 that when I plug it into this function gives me w equals 0. Does that make sense? That's by the intermediate value theorem. Yes, no, maybe?
Yes.
Yes, one yes. All right. No issues with that? Don't have to do the full verification because we're just interested in showing that it has that one value that works. All right, last problem for the day. Here we go. We want to find all values of A that make this piecewise function continuous for all real numbers. Any thoughts?
To make it continuous, like, could you maybe plug -1 into the top one and then see how you can change the bottom one to fit that result?
Yeah, that seems like a decent idea. That's basically what we're going to do. We're going to do it in a little more technical terms, though. So first off, if you plug in -1 to this function, what do you get? If you plug it into the x cubed plus 3x squared plus 3x plus 1 over x plus 1, what do you get?
I think 0 over 0.
Yep, you get 0 over 0. So that's going to be an issue, right? We can't turn ax plus 5 into 0 over 0. So we're going to have to sort of look at this idea of the definition of continuity and think about what it means for a function to be continuous for all real numbers. So if you look at x cubed plus 3x squared plus 3x plus 1 over x plus 1, it's continuous on what interval? Just this piece of it. If we ignore the restrictions and all that, where is it continuous?
Everywhere but -1.
Everywhere but -1. That's another rule you're going to want to know, that a rational function is continuous for all real numbers except the numbers that make the denominator equal 0. So in that case, in this case, that's -1. So we know that already that our function is continuous for everything except at -1. So then our goal is to make it continuous at -1. And so if we're looking at continuity at a point, that's what we're looking at here, continuity at a point, we need to have 3 criteria be met. The first is what?
The function is defined at the point.
Yeah, it has to be defined at the point. So let's see, what is f of -1? Do I use the top or do I use the bottom for that? The cubic, or the rational function or the linear function? When x equals -1, what do I use?
The linear.
Right, the linear piece, right? So that should be -a plus 5. So does f of c exist? Does f of -1 exist? Yep, it's -a plus 5. The second thing is, does the limit as x approaches -1 exist? What do I use for approaching -1? The rational function or the linear function?
The rational.
The rational function, because that's when x doesn't equal -1. And so that's where I'm approaching it from that function. So we already said that that's 0 over 0. So let's factor the top. The top factor is using the binomial theorem, Pascal's triangle, all that fun stuff. To x plus 1 cubed, and then over x plus 1, giving us the limit as x approaches -1 of x plus 1 squared. And what does that equal? If I plug in -1 to that, what do you get?
0.
0. So does that limit exist?
Yes.
Yep. 0 is a number, right? That limit exists. So the function exists, the limit exists. And the third criteria is that the function's value has to equal the value of the limit. So negative a plus 5 has to equal 0, which gives us an a value of what?
5.
5. And so a equals 5 is the only real number value that will make this function continuous for all real numbers. It sort of plugs in that hole that we get from the rational function. Any questions on that?